September 21st, 1942. Boeing Field, Seattle. The largest bomber ever built sits at the end of the runway, engines rumbling. Inside the cockpit, test pilot Eddie Allen runs through the checklist one more time. His crew is nervous, and they have good reason to be. This aircraft weighs 105,000 pounds fully loaded. That's 70% heavier than a B-17 Flying Fortress. And unlike every other American bomber in the sky, when Allen releases the brakes and this machine starts rolling, its nose won't be pointed at the sky. It will be level with the horizon. The B-29 prototype has something no heavy bomber has ever carried. 2 wheels mounted side by side on a single strut extending from the nose. Not a small tail wheel in the back forcing the fuselage into a tail-high stance. A nose wheel. A massive, dual-wheeled nose gear designed to support more than 15 tons of aircraft. Every engineer at every other aircraft manufacturer in America had looked at Boeing's plans and reached the same conclusion. It won't work. The gear will collapse. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The aircraft will ground loop on landing. Pilots won't be able to see over the nose during taxi. The design violates 30 years of accepted wisdom about how heavy aircraft should sit on the ground. Boeing is betting $3 billion, the most expensive military program in history, more than the Manhattan Project itself, that everyone else is wrong. Allen advances the throttles. The 4 Wright R3350 engines roar to full power. The B-29 begins its takeoff roll, nose level, tail level. The entire aircraft parallel to the runway as it accelerates. No tail dragging behind. No high angle of attack at rest. Just a clean, stable platform rolling faster and faster until the wings generate lift and the bomber climbs into the September sky. The flight lasts 75 minutes. Allen puts the prototype through basic handling tests, checking control response, engine performance, systems, integration. But the real test comes at the end when he lines up for landing. Every bomber pilot in the Army Air Forces knows how to land a B-17 or B-24. You come in nose high, let the tail wheel touch first, then gently settle the main gear. Get it wrong, and the aircraft can swing violently sideways in a ground loop, tearing off landing gear, crumpling wings, sometimes cartwheeling the entire airframe into a fireball. Allen brings the XB 29 inches level. Nose wheel and main gear touch almost simultaneously. The aircraft rolls straight down the center line. No swing, no swerve. No pucker factor for the crew wondering if physics will betray them in the last 3 seconds of flight. When Allen taxis back to the ramp, Boeing engineers swarm the aircraft, measuring tire pressure, checking strut compression, inspecting the gear doors. The nose wheel strut has held. The gear has absorbed the impact of a 52-ton aircraft hitting concrete at over 100 miles per hour. But nobody's celebrating yet, because Seattle to Tokyo is 5,000 miles, and the men who will fly this bomber into combat won't have Eddie Allen's 10,000 hours of experience. They'll be 22-year-old kids from Kansas who've never seen an aircraft this big, trying to land on a steel mat runway on a Pacific island while enemy fighters try to shoot them down. The real question isn't whether the gear can handle one test flight, it's whether it can handle hundreds of combat missions flown by pilots who learned to fly in Piper Cubs 6 months ago. Let's rewind to 1938. Boeing is a regional aircraft manufacturer, well-respected but not dominant. Their B-17 Flying Fortress is entering service, but it's a conventional design. Pilots sit in a greenhouse canopy 10 feet off the ground when the aircraft is parked, nose pointed skyward at a 15-degree angle. Standard configuration, same as every bomber since World War I. Then the Army Air Corps publishes a specification that makes every aircraft designer in America recalculate everything they know. They want a super bomber, 20,000 pounds of bombs, range of 4,000 miles, speed of 400 miles per hour, pressurized cabin for high-altitude flight, and, oh, by the way, it needs to be ready for production by 1942. Boeing's engineering team, led by Edmund Allen and George Scherer, sits down to design an aircraft that can meet these requirements. They start with fundamentals. A 4,000-mile range means enormous fuel tanks. 20,000 pounds of bombs means massive bomb bays. Pressurization means a sealed fuselage. 400 miles per hour means aerodynamic perfection. Everything has to be sleek, retractable, enclosed. The design that emerges, Model 345, is revolutionary in a dozen ways. Pressurized crew compartments connected by a crawl tunnel over the bomb bays, remote-controlled gun turrets operated by computer, a wing designed with the thinnest practical airfoil for high-speed flight, and buried in the engineering drawings, almost overlooked in the cascade of innovations, a single decision that will change military aviation forever. Tricycle landing gear with dual nose wheels. The engineering logic is straightforward. The B-29 is going to weigh twice as much as a B-17. A tailwheel configuration puts most of that weight on two main gear struts. That's manageable, but it creates problems. First, the aircraft sits tail down at a steep angle. Fine for grass fields, terrible for visibility when taxiing on a crowded airbase. Second, a tailwheel makes the aircraft directionally unstable on the ground. The center of gravity is forward of the main wheels, which means any swerve during landing tends to amplify rather than self-correct. Pilots call it a ground loop, and it's killed more bomber crews than some combat missions. Third, and this is the killer for an aircraft as large as the B-29, a tail-down stance limits how hard you can brake. Apply too much brake pressure, and the aircraft's momentum pivots it forward onto its nose, a maneuver called a nose-over. This destroys the aircraft and usually kills the crew. Conventional gear means you're always balancing on the edge between inadequate braking and structural catastrophe. The solution, Boeing's engineers argue, is to put a wheel under the nose instead of the tail. Move the center of gravity behind the nose wheel but ahead of the main gear. This makes the aircraft directionally stable. Any swerve on landing tends to self-correct because the steering point is forward of the center of mass, like pushing a shopping cart instead of dragging a wheelbarrow backward. The nose-level stance gives pilots visibility during taxi. The gear geometry means you can brake hard without nose-over risk because the aircraft's weight is already over the main gear. And from an aerodynamic standpoint, a tricycle aircraft can retract its landing gear more completely, reducing drag, which is critical when you're trying to squeeze 4,000 miles out of a finite fuel load. But there's a problem, and it's a big one. No bomber in the world is using tricycle gear. The few aircraft that have tried it, small experimental planes, light transports, have used a single nose wheel. The B-29 will weigh 52 tons when loaded for combat. Can a single nose wheel handle that load? The math says no. The tire pressure required would be so high the wheel would sink into anything softer than concrete. Runway surfaces in the Pacific, where this bomber will operate, are often pierced steel planking or crushed coral. A narrow, high-pressure nose tire would punch through like a nail. Boeing's answer is to double it. 2 wheels, side by side on a single nose strut. This spreads the load, reduces ground pressure, and provides redundancy. If one tire blows, the other can handle the weight long enough to stop safely. It's an elegant solution to an unprecedented problem, and it makes the B-29 the first aircraft in history with dual nose wheels. Of course, it also makes Boeing the target of skepticism from every experienced pilot and engineer in the Army Air Forces. The official objections fill 3-ring binders. The nose gear will shimmy at high speed, the extra weight will cut into bomb load, the complexity will increase maintenance hours. Pilots trained on tail draggers won't adapt, the gear doors won't seal properly. The list goes on. But the loudest objection, the one that keeps Army Air Forces generals awake at night, is simpler and more visceral. It looks wrong. 30 years of aviation experience say a big aircraft should sit tail down. Nose high is safe. Nose level feels like the aircraft is tipping forward, one gust of wind away from falling on its face. The instinct runs deep. Every pilot who learned to fly in the 1930s learned it in a tail dragger. The nose wheel configuration isn't just unfamiliar. It contradicts muscle memory developed over thousands of hours of flight time. Boeing responds with data. They run stress analysis on the gear struts. They calculate load distribution during landing. They model gear dynamics during crosswind touchdowns. The numbers work. The nose gear will hold. It will be stable. It will function reliably. But numbers on paper don't convince pilots who've seen B-17 seconds ground loop on icy runways, who've watched bombers nose over during heavy braking, who've landed tail draggers through combat damage and engine failures and blinding weather. What convinces them, eventually, is the alternative. By 1941, war in Europe has demonstrated that strategic bombing requires enormous aircraft losses to achieve strategic goals. The British are losing bombers at unsustainable rates. The Germans are pulverizing RAF airfields. America's entry into the war, which everyone knows is coming, will require sending heavy bombers over vast distances to strike industrial targets defended by thousands of anti-aircraft guns and fighter aircraft. The casualty rates will be staggering. Anything that increases operational safety, even marginally, will save lives. If tricycle gear makes landing safer, if it prevents ground loops and reduces landing accidents, if it allows pilots to taxi more safely on crowded, dimly lit bases, then the innovation isn't just clever engineering, it's a moral imperative. On January 6, 1942, 3 months after Pearl Harbor, the Army Air Forces places an order for 14 prototype B-29 seconds and 250 production aircraft. The order will eventually grow to 3,900 aircraft, the largest procurement in aviation history, and every single one will have dual-wheeled tricycle landing gear. There's no fallback option. No tailwheel variant for conservative pilots. Boeing has bet the company, and the Army Air Forces has bet the war, that this unproven configuration will work under combat conditions. The first production B-29 seconds begin rolling off assembly lines in July 1943. Wichita, Renton, Omaha, Marietta. 4 massive factories producing bombers as fast as American industry can rivet aluminum and install engines. The pace is frantic. Curtis LeMay, who will eventually command all B-29 operations in the Pacific, visits the production lines and watches aircraft being completed at a rate of 1 every 4 hours. This isn't careful craftsmanship, it's industrial warfare, and every aircraft needs a crew. 22,000 B-29 pilots, co-pilots, bombardiers, navigators, flight engineers, radio operators, and gunners, trained in months, not years. Most have never seen a tricycle gear aircraft before they report to training. Their flight instructors learned to fly in tail draggers. The training manuals are written from scratch because no manual exists for teaching someone to land a 52-ton bomber with nose wheel landing gear. The transition is rougher than Boeing anticipated. Pilots trained on B-17 seconds and B-24 seconds approach the B-29 expecting it to handle like a scaled-up version of aircraft they know. It doesn't. The landing technique is completely different. In a tail dragger, you come in nose high, stall the aircraft just above the runway, let the tail wheel touch first, then gently lower the nose. In a tricycle aircraft, you come in level, with the aircraft still flying, flare slightly to arrest descent rate, and touch down with all 3 gear nearly simultaneously. Get it wrong, land nose low with too much airspeed, and the nose gear hits hard. The strut compresses, the aircraft bounces, the pilot overcorrects, and you're in a pilot-induced oscillation, the aircraft porpoising down the runway with the nose gear slamming into concrete hard enough to crack bulkheads. Or land too slow in a nose-high attitude, and the tail strike bumper hits the runway, a hydraulic shock absorber Boeing installed specifically because they knew inexperienced pilots would misjudge the landing flare. The accident rate during training is staggering. 40 B-29 accidents per 100,000 flight hours. Compare that to 2 accidents per 100,000 hours for the modern Air Force, and you understand what frantic wartime production and rushed training cost. Not all the accidents are landing related. The R-3350 engines catch fire with horrifying regularity, but enough involve landing gear failures, hard landings, and pilot error on touchdown that some Air Force generals quietly wonder if Boeing's unconventional design was a mistake. But the alternative statistics tell a different story. The B-24 Liberator, which has a tricycle gear with a single nose wheel, logs 35 accidents per 100,000 flight hours. The B-17 Flying Fortress, with conventional tailwheel gear, logs 30 accidents per 100,000 hours. The B-29's 40 accidents per 100,000 hours is higher, but that's because the B-29 is an order of magnitude more complex, with pressurization systems, remote gun turrets, reversible propellers, and 4 temperamental engines that require constant management. When analysts break down the accident data by cause, they find something remarkable. Ground loops, the directional control disasters that plague tailwheel aircraft, are almost non-existent in the B-29. The tricycle gear's directional stability is working exactly as Boeing predicted. Crosswind landings, which can be fatal in a B-17, are manageable in a B-29 because the nose wheel keeps the aircraft pointed straight. Hard landings still happen. Pilot skill varies wildly in wartime, but the consequence of a hard landing in a B-29 is usually a damaged strut and a maintenance delay, not a cartwheeling wreck and a dead crew. The nose gear absorbs punishment that would have destroyed a tailwheel, then gets repaired by Cleveland Pneumatic's robust spare parts supply. By late 1943, the 58th Bombardment Wing begins deploying to India for combat operations. The first crews to fly combat missions in the B-29 have an average of 400 hours of multi-engine time. The desired number was 400 hours. Only 10% have overseas experience. Most have never landed on anything except a paved runway in Kansas. Their destination airfields are in India and China, carved out of jungle and rice paddies, with runways made of crushed stone and prayers. The climate is brutal. Monsoon rains turn airfields into mud bogs. Heat and humidity warp control surfaces and corrode hydraulic lines. And the Japanese know exactly where these airfields are, sending bombers to crater runways and fighters to strafe parked B-29 seconds. On June 15, 1944, 68 B-29 seconds take off from bases around Chengdu, China, for the first raid on the Japanese home islands since the Doolittle raid in April 1942. 47 bombers reach the target, the Imperial Iron and Steel Works at Yawata, and drop their bombs through heavy anti-aircraft fire. One B-29 is lost to flak. Another makes an emergency landing in China and is destroyed on the ground by Japanese fighters. A third crashes returning to base. But 56 bombers make it home. 56 crews land safely on primitive runways, in darkness, with fuel gauges reading near empty, and none of them ground loops. None of them nose over during heavy braking. None of them swerves off the runway because the pilot couldn't see the centerline from a tail-high cockpit. The tricycle gear does exactly what Boeing promised. It gets the crews home alive. The real validation of Boeing's gamble comes later that year, when B-29 operations shift to the Mariana Islands. Saipan, Tinian, and Guam are secured by August 1944, and Navy Seabees immediately begin constructing the largest air bases in the world. Each island gets multiple runways, some over 2 miles long, designed to handle hundreds of B-29 sorties per day. The operational tempo is punishing. By November 1944, B-29 seconds are flying missions to Tokyo, a round trip of 3,000 miles. Aircraft take off every few minutes, fully loaded with fuel and bombs, rolling down runways that are often still under construction. They return 12 to 14 hours later, many with battle damage, some with wounded crew, all with fuel gauges showing fumes. This is where tricycle landing gear proves its worth in ways Boeing's engineers never anticipated. A damaged B-29 limping home on 3 engines, hydraulics failing, crew exhausted, needs to land immediately. There's no time for perfect technique, no opportunity for a second approach. The pilot brings it in however he can, and the landing gear has to absorb whatever punishment the landing delivers. On Tinian, crews watch a B-29 return from Tokyo with the entire right wing shredded by anti-aircraft fire. The aircraft is flying crooked, one main gear won't extend, and the pilot has no hydraulic pressure for brakes. He brings it in on the nose wheel and left main gear, the right wing dragging on the runway in a shower of sparks. The aircraft slides 1,500 feet before stopping. The nose gear strut, bearing twice its designed load, holds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The crew walks away. Another aircraft returns with the tail gunner dead and the bombardier wounded. The pilot is 23 years old, with 200 hours in the B-29. He's never landed with battle damage. Tower talks him through the approach. He comes in too fast, touches down 2,000 feet down the runway, realizes he won't stop in time, and applies full brakes. A B-17 would have nosed over. The B-29's weight distribution keeps the tail down, the brakes lock all the wheels, and the aircraft slides to a stop 50 feet from the runway overrun. Mechanics find the brake assemblies glowing red-hot, but the nose gear is intact. The statistics from Mariana's operations tell the story that individual incidents only hint at. From November 1944 through August 1945, B-29 seconds based in the Marianas fly over 33,000 combat sorties. The average mission duration is 14 hours. The average landing weight is over 100,000 pounds. These are not training flights with perfect conditions. These are combat-damaged aircraft flown by exhausted crews landing in crosswinds, rain, and darkness. The landing accident rate during this period is 4%. That means for every 100 B-29 seconds that land, 4 have some form of landing incident. Blown tire, collapsed gear, runway overrun, hard landing requiring inspection. But the aircraft total loss rate from landing accidents is under 1%. The gear can be damaged and still get the crew on the ground safely. Once stopped, maintenance teams replace struts, swap wheels, patch hydraulic lines, and have the aircraft ready for the next mission. Compare this to earlier bomber operations. At Guadalcanal in 1942, the Marines operated from Henderson Field, a dirt strip constantly under attack. Aircraft routinely ground-looped on landing because the runway surface was uneven and tailwheel aircraft couldn't track straight. Some missions saw 20% of returning aircraft damaged in landing accidents. The operational availability rate, the percentage of aircraft ready for combat at any given time, was often below 50%. Tinian operates 500 B-29 seconds with an operational availability rate above 75%. Part of that is logistics, better maintenance, more spare parts. But part of it is the fundamental robustness of Tricycle landing gear. You can damage it and still land safely. You can repair it quickly. And you can train new pilots to land it without the weeks of tail dragger training that creates ground loop muscle memory. Curtis LeMay, who takes command of XXI Bomber Command in January 1945, understands this better than most. Before the war, he flew B-17 seconds. He knows what it's like to land a tail dragger in a crosswind with battle damage. When he arrives in the Marianas and sees the B-29 operation, he immediately changes tactics. Previous doctrine called for high-altitude precision bombing. Fly at 30,000 feet above enemy fighters. Use the Norden bomb site for accuracy. LeMay looks at the results. Terrible accuracy due to jet stream winds, low tonnage due to the fuel cost of climbing to altitude, and makes a radical decision. Strip the defensive armament, fly in at 5,000 to 8,000 feet, and drop incendiary bombs at night. The change works. Bombing accuracy increases dramatically. Tonnage delivered per sortie triples. But it also means B-29 seconds are now flying through searchlights and anti-aircraft fire at altitudes where a single hit can be catastrophic. The first low-altitude incendiary raid on Tokyo, March 9th through 10th, 1945, costs 14 B-29 seconds shot down and 42 damaged. The damaged aircraft returned Tinian and Saipan with holes in wings, shrapnel damage to control surfaces, hydraulic systems leaking, and electrical systems sparking. Every single damaged aircraft has to land safely or the crew is lost. The tricycle gear becomes the last line of defense. If the gear holds, if it absorbs the landing loads despite damaged hydraulics or blown tires, the crew survives. If it fails, the aircraft cartwheels and everyone dies. It holds. Mission after mission, month after month, the gear takes punishment that would have been unthinkable in 1942. Pilots land with no hydraulic pressure, using the mechanical backup system. They land with one main gear stuck in the up position, balancing on nose wheel and one main strut. They land gear up on the runway, the airframe sliding on its belly while the crew braces for impact, and the gear mechanisms, protected by the fuselage structure, often remain repairable even after the belly skin is ground away. The Pacific War ends in August 1945, with 2 atomic bombs delivered by B-29 seconds. Enola Gay and Bockscar, both silverplate variants, modified for nuclear weapons, land safely after the most significant bombing missions in human history. The Tricycle gear that Boeing engineers sketched in 1938 has just delivered weapons that change warfare forever. But the story of the B-29's landing gear doesn't end with the war. The design establishes a template that becomes standard for every large aircraft that follows. When Boeing begins designing commercial airliners in the late 1940s, the 377 Stratocruiser uses Tricycle gear derived directly from B-29 technology. The B-47 Stratojet, America's first swept-wing bomber, uses bicycle landing gear with outriggers, but the nose-forward weight distribution comes from B-29 experience. The B-52 Stratofortress, which enters service in 1955 and remains operational in 2025, uses a unique crosswind landing gear system, but it's still fundamentally Tricycle. 8 wheels on 4 bogies under the fuselage, and 2 small outrigger wheels near the wingtips. The weight distribution, the directional stability, the operational logic, all trace back to the B-29. Soviet engineers, who reverse engineer 3 B-29 seconds that make emergency landings in Siberia during the war, create the Tupolev Tu-4. It's a bolt-for-bolt copy, including the dual nose wheel Tricycle gear. Stalin's engineers, who'd spent years developing tailwheel bombers, suddenly have access to Boeing's design and realize the Americans have been right all along. The Tu-4 becomes the foundation of Soviet strategic aviation, and every bomber that follows uses Tricycle gear. By 1950, Tricycle landing gear is standard on all new military aircraft and most commercial transports. The last large tail-dragger bombers, the B-29's contemporaries like the British Lancaster and the German Hay 177, are retired and never replaced with tail-wheel successors. The transition is total and irreversible. What makes this remarkable is that the transition happens in less than a decade. In 1940, tail-wheel landing gear is universal doctrine. By 1950, it's obsolete for anything larger than a small private aircraft. The B-29 doesn't just introduce Tricycle gear. It proves the concept so thoroughly under the worst possible conditions, combat operations across the Pacific, that no other configuration can compete. The dual nose wheel innovation becomes standard for heavy aircraft. The C-5 Galaxy, which enters service in 1968, uses a 4-wheel nose gear to support its 840,000-pound maximum takeoff weight. The Boeing 747, introduced in 1969, uses a 2-wheel nose gear derived from the same load distribution principles Boeing pioneered with the B-29. Modern airliners, military transports, even the Space Shuttle, which lands as a glider with no engines, all use nose wheel Tricycle configurations because the B-29 proved it works. But beyond the technical legacy, the B-29's landing gear represents something more fundamental about how innovation succeeds in crisis. Boeing's engineers had data showing Tricycle gear was superior. They had calculations proving it would work. But data doesn't change minds when it contradicts 30 years of experience. What changes minds is demonstrated success under conditions where failure means death. The Army Air Forces didn't adopt Tricycle gear because Boeing's math was elegant. They adopted it because pilots kept bringing shot-up B-29 seconds home, landing them safely on primitive runways in weather that would have destroyed tail draggers. The gear worked when it mattered most, and that success created the credibility that made institutional change possible. Consider the alternative timeline where Boeing builds a conventional tailwheel B-29. It's technically feasible. The engineering would have been simpler. Pilot training would have been easier because instructors already knew how to teach tail dragger technique. The prototype would have flown sooner, with fewer development problems. But that aircraft wouldn't have been as safe. The ground loop accidents would have been higher. The landing incident rate on primitive Pacific runways would have been worse. More crews would have survived combat only to die in landing accidents. The operational availability rate would have been lower, meaning fewer sorties, less tonnage delivered, possibly a longer war, and the post-war aviation industry would have been different. Commercial aviation would have eventually transitioned to tricycle gear. Someone would have made the leap, but the transition would have been slower, more tentative. Airlines would have worried about pilot training costs, about passenger perception, about the reliability of unproven technology. Boeing's wartime demonstration removed all doubt. If tricycle gear could handle combat operations in the Pacific, it could certainly handle commercial flights between New York and Los Angeles. There's a photograph from Tinian, August 1945, that captures the moment. A B-29 sits on the hardstand, ground crew swarming around it, checking engines, loading bombs, refueling. The nose gear strut is clearly visible, 2 wheels side by side, gleaming in the tropical sun. Behind it, another B-29, and another, a line of bombers extending down the taxiway as far as the camera can see. Each of those aircraft weighs more than most buildings. Each will fly 3,000 miles, drop 10 tons of bombs, and return safely. And every single one depends on a landing gear configuration that, 7 years earlier, Boeing proposed over the objections of nearly everyone in the aviation industry. Eddie Allen, who flew that first prototype in 1942, died in February 1943 when an B-29 caught fire during a test flight and crashed into a meatpacking plant in Seattle. He never saw the B-29 inches combat, never saw the gear system he'd tested prove itself over 30,000 sorties, never knew that his test flight had validated a design that would become standard for 75 years and counting. But the pilots who flew combat missions from the Marianas knew. The crews who brought damaged aircraft home and walked away from hard landings knew. The maintenance chiefs who replaced gear struts and sent aircraft back into combat 12 hours later knew. Boeing had built something that worked exactly as promised when it mattered most. The B-29 Superfortress was retired from frontline service in the early 1960s. The last variants, converted to tankers and weather reconnaissance aircraft, flew until 1965, but the landing gear design it pioneered remains operational on thousands of aircraft worldwide. Every time a 747 touches down at LAX, every time a C-17 lands at a forward operating base, every time an A380 rolls to a stop after crossing an ocean, Boeing's 1938 innovation is there, invisible but essential. Some innovations are visible. Jet engines, swept wings, digital flight controls. These changes are obvious to anyone watching an aircraft fly. Other innovations are structural, fundamental, so successful that they disappear into the background of how things work. Tricycle landing gear is that kind of innovation. It's the foundation that makes everything else possible. And it started with a group of Boeing engineers who looked at the requirements for a superbomber and realized that the conventional wisdom about how aircraft should sit on the ground was wrong. They designed something better, fought for it against institutional resistance, and proved it in the harshest test imaginable. The result is flying overhead right now. You just don't notice it anymore because it works so well. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.